Hello, everyone. My name is Payman Samadi. I'm from Inno.ai. I'm going to speak about designing private cellular networks. Quick intro about me. I spent 10 years of my career building optical switches for high-performance computing before entering the wireless world. And now I've been in this world for the past 7 years. But when we talk about any technology, the first question is why use that technology? Basically, what are the use cases there? For private cellular, we could think about the cases that we have mobility and the cases that we want to provide more coverage and more control with less hardware and less cabling. So you could think about an industrial IoT. If you have a manufacturing facility, if you have a warehouse, you have autonomous lift trucks that are moving around. That would be a good use case that you have there. You could think about public safety and emergency. If you have mission-critical applications, that would be a good use case. If you think about construction zone and mines, then when you have these remotely controlled vehicles there, that could be a good use case. And maybe soon, if our laptops all have eSIM capability, that would be a new world that we could use private cellular there. Since most of these networks are built outdoor, and it's a bit different from indoor Wi-Fi that we all always used to it, I'm going to talk a little bit about the design consideration there. When we build a network outside, we're building it on the ground, and Earth is now flat. We have ups and downs, we have elevations there, and we call it the terrain. We need a digital model to understand where the Earth goes up and down, and that's called the DTM model. And then on top of that, we have a surface. That on that surface, we could have trees and greenery. We could have all sorts of obstructions and buildings, which is quite important there. And that digital model called DSM. So to show an example, this is a manufacturing facility. We have an area around it that basically we want to provide a network. And if I go here and basically I run my 3D model, what I'm trying to do here, understand where are my trees, where are my buildings, and basically what are they consist of, and how high they are, what's the type of material that you have. So this is created now. If I go on 3D, you're able to see that, okay, I have these trees here that are going up, I have these buildings here, and we need to be able to differentiate that. Okay, this building is concrete because in terms of attenuation, it's going to be different. In terms of reflection is going to be different. When we look at these trees, what type of trees we have? If we have the trees that have more canopy versus the trunk, how is going to be attenuation inside that canopy just on the month that we're going to go? So these are all the things that we need to consider there. Once we go from there, where is my second one? We need to talk about the concept of carrier, which is basically how the spectrum is used on the radio. We have TDD and FDD. In TDD, we have different time slots that we put the signal on top of it. And the uplink and downlink could be chosen on how many time slots we want to put there. It's different on FDD, that it's based on the bandwidth that each uplink and downlink is associated to it. So to show you an example, how does that work? So if I go here, I have this AP here. It's an outdoor Cellular AP11. I have defined a carrier. Define the band, it's B48 CBRS, how much bandwidth I have, 20 megahertz, my subcarrier spacing, how's my uplink and downlink split, in terms of modulation format that I support, and MIMO for downlink and uplink, how that's going to be. And then I need to add an antenna, which is usually external there, so we have different types of sectors. When we build these sectors, especially with directional antenna, we need to apply some sort of carrier there. So, okay, this sector, I'm using this directional antenna, it's at 8 meter high, and I'm using this C1 carrier here. So once I use that, I'm able to go and basically place this AP here, and based on that, see how my signal looks like. Let me just go back there. But the signal propagation, sorry, it doesn't show my whole. The signal propagation, when we do cellular, because we could do much lower signal levels, there are a few other things that are important. When we do indoor Wi-Fi, we're mostly interested in line of sight, maybe reflections, but when we do cellular, reflections becomes extremely important because if we are in a manufacturing facility and we have a lot of instruments that have metal, we're going to have a lot of reflections coming out of it. If you're outdoor, if you're in a port, and we have a lot of containers that are metal, we're going to have a lot of reflections. Buildings, the same way. There's also a concept of diffraction. Basically, you've seen you get your cell phone, you go behind a building, and your cell phone works, otherwise there's no direct signal. It's because of diffraction. Basically, when the waves reaches the edges, it becomes many other rays, and then it goes down, and based on the angle that you have, and based on the type of material, and the distance, you're going to have a received power there. So if I go back here, you see I've put my AP here, I have all these signals, and I have all these phenomena. If I remove my diffractions here and say, okay, I don't want to see my diffractions here, suddenly you will see that a lot of these coverage that I had here are basically gone. If I remove my reflections there, if you look at this side here, you see I have a lot of power here, and all of these are gone because it was reflected from this building. So it's quite important that we consider all of these when we go and do the design. Once we get to the design, we have this concept of RSRP. In Wi-Fi, we mainly use RSSI, which is our in-band power. In cellular, we have the RSRP, which is the amount of signal that is spread over the bandwidth that we have, which they call it like resource elements. This number of resource elements, it depends on the technology we use. If you use LTE and 5G, it's different. Basically, we have these resource blocks that are 12 subcarriers are OFDM, and then you have these 14 of the symbols of OFDM, and one of those is RSRP. The next thing to consider is our SINR, because we may have a lot of signal coming, but how much of that signal is really good? We have a lot of interference based on the number of the radios they have and what channel they use. So this is a very good indicator to show us how it's basically the quality of our signal. In terms of how good is good, basically similar to RSSI that we have our Wi-Fi. If you're about minus 80 dBm, 20 SINR, that's quite great. And we could go as low as minus 105 generally and positive SINRs there, and that works for most of the use cases, depending on the device, of course. Minus 100, you could be safe there, and that's the consideration you need to have. But when we talk about SINR and interference, we need to talk about the spectrum allocation and spectrum planning as well. So when we talk about CBRS, which is this 350 megahertz, you do not have access to all of it all the time. You cannot just openly use that. Depending on who else has used this, you might end up having only 20 megahertz or 40 megahertz. If you only have one sector, one radio, you could just put it and put as much bandwidth as you want to put. There's no problem there. But if you have multiple sectors and multiple radios there, then it's important how to assign it. If you put that 40 megahertz that you have available on each of those radios, then you need to be very careful about your interference, how they're overlapping there, and if I'm receiving signal from the first radio, second radio, and then I have basically no signal there. Another option is that, okay, I don't want to use the whole 40 megahertz all the time. I divide it to 220 megahertz, and on my 4 sectors, I use 20 on each. Now I have less capacity, but I have less interference. So it's all about what is your use case, what type of antennas you're using, and based on that, you could find what's the best thing for you. We have this concept of carrier aggregation. You could have multiple carriers combined to one sector, so you have more spectrum coming, but then at the same time, if you use the same carrier somewhere else, that could be a problem. Let me show you an example here. So on this radio, I have one carrier, it's 20 megahertz bandwidth. I'll go ahead and the second one, and I have the same power here as I had before, and I choose my uplink downlink 2 to 1 here, which is not that important there. And from here, I go and add a second sector, which is my second antenna. I put it 8 meters, put my azimuth on 180, and I have my C2 here, and I update my AP. And now I have 2 sectors, both working on the same carrier as we have there. This is our SRP, but we could go and look at our interference there. So as you could see, I have a little bit of interference happening because they are both using the same channel there. But I could do something else. I could come here and say, don't use 3580 there. Do use 3560 on my basically C1. And now the full screen is not working. Zoom out. Okay, and I could update there. And once I update there, now I have much less interference because I'm using complete two different channels there. So it's just about how much they're overlapping. If they're pure like hat or Gaussian, that they have some coverage that they go there. There's the other thing to consider. We talked about carrier aggregation. So what if I go and say this sector, I'm going to have 2 carriers there, so I'm going to have 40 there. And I update that. Basically, now what I'm going to receive is that one of my sectors have 2 carriers, one has 1, and because of that, I'm getting this amount of interference. But I could look at my throughput stuff, and then I'll see, okay, I get much more throughput there because of this carrier aggregation compared to the other case that I had there. Let me make sure. Let me just refresh my screen so the Zoom works fine. So I'm going to go over a few basically real-life use cases. Actual sign. And I'm going to go over basically showing a few use cases that are very critical for our for private cellular. The first one that I'm showing here is basically a mine. So mines are a very interesting use case because these open-air mines, they move a lot. They change a lot based on how they are. Let me just make sure this is on. And you start basically building these mines, and then as the time goes, you're going to have change that happens there, and you're going to have these new things that happens there. So they continuously add more images, usually get by drones coming, and you could see how basically this one real mine looks like. You have this pit here that goes all the way 50 meter down. The whole size is about 1 kilometer. You have lots of ups and downs happening there. And this is continuously changing. And you need to have connectivity there, as I mentioned, for the use case of a lot of remote control of construction devices. My drones that are going there for imagery and topography that we have there. And if you want to build this with Wi-Fi, with the changes in cables, it's going to be quite hard. Private cellular is a very good solution here. I could add 2 private cellular radios here, and I could crank up the power there because this is CBRS. I could go up to 40-something, 48 or 9, and I could cover majority of these. Pretty good signal everywhere, which is a very good use case as we have there. Another use case to talk about is indoor when we have a plant. So this is basically a plant that we have for industrial use cases. We have this open space, we have some buildings. I've just put the layout there. And what I'm trying to show here that if we design this with private cellular versus Wi-Fi, how different it could look like. So just parsed my layout, and I have my walls and everything there. And from here, I talked about these very sectorized APs. So one example of it is this AirSpan 1500. Once you face it down, you're going to have very good coverage there. And I could go up to 33 dBm, and let me see if I design it with this private cellular, how it's going to be different. The point we're making here is not that it's going to be fully replaced, because there's a lot of consideration has to be done in terms of how much spectrum I have, how much would be my interference there. But we're going to show that you could have much less number of APs, much less amount of cabling, and be able to still get a very good network. Here, The platform for a quick design told me I need 7 APs. If I go and see my coverage map, each is supporting about 653 square meters, which is pretty good. My secondary looks good, and my Cellular looks good with these 7 ones. And then I've already designed this with Wi-Fi. I could go over the Wi-Fi. This is the Wi-Fi design. I have about 36, and each AP is covering about 127 square meter. So again, making a decision based on the use case, is this a better solution for me, or is the other solution better for me? Another use case I want to talk about, which is quite important, is spatial events. We have many places, for example, concerts, music festivals, any sort of outdoor sport activity that it's for a short period of time. It happens in a remote location that you want to have connectivity there for 3 weeks, and you want to have it from day one. There's a lot of change happening. There's a lot of construction happening. You can't have a lot of cabling coming and going there, and you wanted to make it fast, and that's kind of one of the very good solutions there. You could have your even backend coming with the fixed wireless point-to-point from 50 kilometers, so you bring the internet there, use a private cellular there to distribute. You have few sectors there, and everything's seen. This is an example of a music festival. It's a real one that happens in Lisbon called Noche Live, and I just created here. I have my stages and my kiosk there and my trees and everything there, and I just overlaid the plan that they have there. And the use case I'm talking about, not still about my consumers going and connecting. I'm talking about our POS system. I'm talking about our video cameras, security, every background network that needs to be run there, and I want to make sure it works from day one. So if you want to build it with Wi-Fi, that would be a quite hard operational task. But here, I've basically put 1 AP, 2 sectors on top of the building there, and as you could see, I have full coverage here. If you want to get an idea about the size of this place, it's about like 500 meters to 500 meters, and I could have all my devices connected there. Soon, we could have QR codes for consumers that they could just put their phone, scan the QR code, have the eSIM installed, and then you could start having the same type of connectivity for consumers as well. All right, to summarize, when we talk about private network planning, we need to really consider environments, both indoor and outdoor. If you're outdoor, it's important to know about our terrain, the elevation of the earth at different locations. It's important to know what is on top of that in terms of all the trees, greenery, buildings, obstructions, know their materials, know their height. Once we go to do our ray tracing, it's very important to do more than line of sight. As I mentioned, if you're indoor and you're in an industrial plant, there's a lot of metal. They have a lot of reflection happening there. You build a network, you go there, and you see everything's different, so it's important to have that. If you're in an urban area and you're having a lot of buildings, probably you have a lot of diffractions. So it's important to consider that, especially when you do your interference calculation. Once we get to our design side, it's important to look at our RSRP and our Cellular. RSRP is basically our received signal. It could be much lower because our device have better sensitivity. And it could go up to -1 of 5, and that's the reason all this secondary effect becomes very important. Cellular is very important because if you're using 20-40 megahertz and you're using the same spectrum there, it's important to make sure that they're not overlapping there. And then once we think about our spectrum planning, if you think about capacity, it's all about our carrier aggregation. If you're thinking about interference, knowing basically how we do our channel reuse. Hope this was useful. Thank you very much.